Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Stress, Strain and Elastic Constants from the paper Ceramics. So the learning objectives of this module are: first, we will be discussing about the stress and strain at a point. Second, the elastic constants of single crystal and also for cubic crystals will be discussed. Thirdly, the elastic constants for polycrystals will be discussed. Lastly, we will also discuss about how does the porosity affects the elastic constants. So students, let us start with a basic introduction about the module. The ceramics as a class of materials, they have very high elastic constants. So this comes from their strong covalent ionic bonding. So in this module, first the concepts of stress and strain as tensor quantities are developed. So then the elastic constants of ceramic single crystals are described. So these are then related to the elastic constants of the ceramic polycrystals. The effect of porosity on the modulus is also discussed. Stress at a point. So students, we are familiar with the definition of the stress as the force per unit area. So thus, if a total force P is acting uniformly on a cylinder of cross-sectional area A as shown in this figure, then the stress on any plane AA passing through the point O and perpendicular to the axis of the cylinder is P by A. However, the stress on another plane BB through the same point O but with its normal inclined at an angle theta to the axis would be P by A by cos theta equal to P cos theta by A. Thus the stress at any point is defined only with a reference to a plane passing through that point. So this figure shows a simple case in which a uniform force acts along the axis of the cylinder. In a general case, the body can be of an arbitrary shape. So the forces acting on it can be acting in different directions. So these can be external forces or body forces. The body forces are those forces which act on each volume element of the body. So thus the force inside the body can vary from point to point. So if delta P is the net force acting on an element of area delta A passing through any point O in the body, then the total stress vector at point O with reference to the plane containing delta A is defined as T equal to limit delta A tends to 0 of delta P by delta A. So as shown in this figure. So the total stress vector is called a traction T. So the value of T is different for different planes passing through P. So to define uniquely the stress at a point, we need to know the stresses acting on three mutually perpendicular elemental planes passing through that point as shown in the below figure. So, the coordinate axes are taken to be parallel to the edges of the parallelopipe. The traction T on the top face of the parallelopipe has been resolved into three components: Tx, Ty and Tz. Tz is the normal stress and Tx and Ty are the components of the shear stress on this plane. The other faces of the parallelopipe would also have three components, each of the stress. So if the coordinate axes x, y, z are denoted by 1, 2, 3 respectively, then the stress in direction x on a face with its normal along the y-axis is denoted as sigma 1, 2. So in general case, sigma ig denotes a stress in direction I on the plane with its normal along the jth axis. So there are 9 sigma ig forming a second rank tensor. So only 6 independent sigma ij components are there. So continuing our discussion over stress at a point. So now to find the stress on any plane passing through the point, knowing these 6 components, let us consider a plane, be the plane ABC, infinitesimally close to the desired point O, which is also a corner of the parallelopipe. Let N1, N2 and N3 be the direction cosines of this plane. Then it can be shown easily that the components of the stress on this plane are S1, S2 and S3, where Si equal to summation over j equal to 1 to 3 over sigma ij. So the total stress S on the plane is given by S square equal to S1 square plus S2 square plus S3 square, and the direction of S is given by its direction cosines S by S1, etc. So it turns out that the stress at a point is a tensor quantity with the components sigma ij. Strain at a point. So we are familiar with the definition of the linear strain as the change in length per unit length. So we are also familiar with the shear strains. Strain is defined in this manner as engineering strains. So in this section, we are describing the strain as a tensor quantity. So consider a line PQ in a body which becomes P prime Q prime after deformation as shown in this figure. So the length delta x1 of PQ has now increased by delta U1. So the linear strain E11 is therefore E11 is the extension of PQ per unit length along the x1 axis, that is delta U1 by delta x1. We similarly define a quantity E21 as E21 equal to delta U2 by delta x1, approximately equal to delta U2 by delta x1 plus delta U1 equal to theta, that is anti-clockwise rotation of PQ. So in general, the element Eij denotes rotation towards I of axis J. So as a rotation can be achieved even by a rigid body rotation and not only by deformation. The quantities Eij includes the rigid body rotation also and the rotation by deformation only. Epsilon is obtained by taking the average of the quantities Eij and Eji, that is epsilon ij equal to half of Eij plus Eji. Elastic constants of single crystals. The familiar elastic constants such as the elastic modulus, the shear modulus, Poisson's ratio, etc. refers to the isotropic materials. The various elastic constants are related so that for an isotropic body, there are only two independent elastic constants. So a single crystal is anisotropic. The number of independent elastic constants is large and depends on the symmetry of the crystal. So if a crystal is subjected to a general state of stress, that is sigma ij, then each of the strain component epsilon ij is related to each of the stress component by this relation epsilon ij equal to Cijkl sigma kl. So this expression denotes a sum in which each of Ijkl are summed over from 1 to 3. That is the Einstein convention. Now total 81 elastic constants are there. Cijkl. Elastic constants of single crystals continued. So however, the total number of independent elastic constants is 21 only, as follows: as sigma ij equal to sigma ji and epsilon ij equal to epsilon ji. So the total number of independent stress and strain components, each is 6 only, and the number of elastic constants Cijkl is reduced to 36. So by considering the energy stored in the body on straining, it is found that Cijkl equal to CKLij, that is the indices can be exchanged pairwise. This reduces the number of independent elastic constants to 21 only. So this number is further reduced when the symmetry of the crystal is considered. So now consider the indices in pairs, that is for Cijkl, consider Ij and Kl. Second, replace each pair by a single index according to the following convention, that is 1 1 can be replaced by 1, 2 2 by 2, 3 3 by 3, 2 3 1 is missing by 4, 3 1 2 is missing by 5, 1 2 3 is missing by 6. So we can write C 4 times 1 equal to C 1 1 equal to C 4 times 2 equal to C 2 2 and C 4 times 3 equal to C 3 3. C 1 1 2 2 equal to C 1 2, C triple 1 2 equal to C 1 6, C double 1 2 3 equal to C 1 4, C triple 1 3 equal to C 1 5, etc. C 1 2 1 2 equal to C 6 6, C 2 3 2 3 equal to C 4 4, C1223 equal to C64, etc. So using the above convention, the 21 independent elastic constants as shown over here can be written. So these are shown as an array in the next slide. The repeated constants are marked bold. So students, this is the array of 21 independent elastic constants for a triclinic crystal, and here the repeated constants are marked as bold. Elastic constants of single crystals, continuing the discussion over it. The number of independent elastic constants is further reduced if the crystal has some symmetry. Now, higher the symmetry, smaller the number of independent elastic constants. So, the number of independent elastic constants for different crystal systems is shown in the next slide. So, continuing our discussion over elastic constants of single crystals, this table shows the number of independent elastic constants for different crystal classes. So students, as you can see over here, that is for class C1, S2 triclinic systems, there are maximum number of independent elastic constants, and below that we have the class C1H, C2, C2H monoclinic system having 13 independent elastic constants, and the minimum number of independent elastic constants occurs for the isotropic crystal class and system. So the array of the elastic constants for the cubic system is shown in this table. Now, for the isotropic system, the array of the elastic constants is same as for the cubic system, but there are only two independent elastic constants with C44 equal to C11 minus C12 by 2. The array for the compliances for the isotropic system is similar with S44 equal to twice of S11 minus S12. Elastic constants of ceramic polycrystals. The structural ceramics are mostly used in the polycrystalline form. It is therefore important to be able to predict the elastic constants of the polycrystals using the elastic constants of the single crystal of the same ceramic. So a simple method to do is to consider the polycrystals as a composite consisting of infinite number of phases with all possible orientations. So various techniques have been developed to determine the properties of the composites from the properties of the constituent phases. A simple way to do is to use the rule of mixtures. The following two equations gives the upper and the lower bounds of the bulk modulus B and the shear modulus mu. These are called as Voigt-Rieuss bounds. That is, upper bound is m equal to m1 v1 plus m2 v2, and lower bound is 1 by m equal to v1 by m1 plus v2 by m2. Now here v1 and v2 are the volume fractions and m1 and m2 is the modulus of interest for the two phases respectively. Now continuing our discussion over the elastic constants for polycrystals, Voigt and Rieuss used similar technique for averaging the elastic constants and obtained the upper and the lower bounds. The void upper bound for the bulk modulus B and the shear modulus mu are given as B equal to C plus 2D by 3 and mu equal to C minus D plus 3E by 5, where C equal to C11 plus C22 plus C33 by 3, D equal to C12 plus C23 plus C31 by 3, and E equal to C44 plus C55 plus C66 by 3. So similarly, the Lewis lower bounds on the bulk and the shear modulus, they are given by the following relations, where B equal to 1 by 3 multiplied by Q plus 2R, mu equal to 5 by 4Q minus 4R plus 3S, where Q, R and S are given by these relations. Elastic constants for polycrystals continued. So the average of upper and lower bounds is called as the VRH average, and this average agrees surprisingly well with the experimental results. Thus, for alumina, experimental value is for E equal to 401 gigapascal and VRH average is 402 gigapascal, and mu experimental is 161 gigapascal and VRH average is 173 gigapascal. So let us now discuss the effect of porosity on the elastic constants of ceramic polycrystals. As the polycrystalline ceramics always have some porosity, it is important to consider the effect of porosity on the elastic constants. It is not fruitful to use the simple composites approach with porosity as one of the phases with zero modulus, because now the lower bounds are 0 and the average value is far from the real value. So some approximate relations are available for this case. For low porosity, assuming the pores to be physical, Mackenzie gave the following expression for the Young's modulus of a porous body, that is E equal to E naught multiplied by 1 minus AP plus BP square, where E naught is the Young's modulus of the dense ceramic, P is the volume fraction of the porosity, and A and B are the constants of order of 1.9 and 0.9 respectively. So for very high porosity, that is P greater than 0.7, the following relations are found to be useful. E equal to E naught 1 minus P the whole square and mu equal to mu naught 1 minus P the whole square, where mu and mu naught are the shear modulus of the porous and dense material respectively. So for intermediate porosities, the relations proposed are not very accurate. So now students, let us summarize what we have learned in this module. Firstly, in this module, the concepts of stress and strain as tensor quantities are developed. The elastic constants of the ceramic single crystals and polycrystals are discussed. The effect of porosity on the modulus is also discussed. Secondly, the stress at any point is defined only with the reference to a plane passing through that point. So this can be obtained if the stresses on three mutually perpendicular elemental planes passing through that point are shown or are known. Thirdly, the component acting along the direction j on a plane whose normal is along the ith axis is denoted by Sij. So there are thus 9 Sij, of which only 6 are independent. They are symmetrical and form a second rank tensor and totally define the stress at a point. Next, the strain at a point is also a tensor quantity and has 9 components, that is Ej, of which only 6 are independent. Then we discussed that if a crystal is subjected to a general state of stress, Sij, then each of the strain component, Ej, is related to each of the stress component, that is Ej equal toCijkl Skl, with Ijkl assumes the values from 1 to 3 and the Einstein convention has been used. Next, we discussed that there are 21 independent elastic constants for a crystal with no symmetry. The number decreases with increasing symmetry. It is 3 for a cubic crystal and 2 for an isotropic body. Then we discussed about the stress components. The stress components are related to the strain components through another set of proportionality constants, Sijkl, called compliances Sij equal to Sijkl Ekl. LikeCijkl, there are 21 compliances for a crystal with no symmetry. So now, by replacing a pair of indices by a single index according to certain convention, the elastic constants and the compliance, they are expressed using two indices, say Cmn. Then we discussed that the elastic constants of the polycrystals, they can be predicted as for the composites using the rule of mixtures with the upper and the lower bounds of the bulk modulus B and the shear modulus mu being given by Voigt-Rieuss bounds as follows, that is m equal to m1 v1 plus m2 v2 and 1 by m equal to v1 by m1 plus v2 by m2. So the average of the upper and the lower bounds is called as the VRH average and agrees well with the experimental results. Next, the effect of porosity. For low porosity, the Mackenzie gave the following expression for the Young's modulus of the porous body, that is E equal to E naught multiplied by 1 minus AP plus BP square. Thank you.